Hello, class. I've just had a lot of trouble trying to get this whole thing to work. Not to mention, I've got coffee half over there that looks like I'm not going to be able to drink it. Today is the first to the last lecture that we're going to have for this class. And I'm going to try to do the second lecture right after this lecture, although I have to do a little work on the problem. I am then going to send you out a 4-problem homework that you're going to complete, and you're going to get back to me by Friday. And predominantly, or I should say entirely, on this new stuff that we have been doing. And then we really have the take-home final at the end, which I will send out to you somewhere around the 10th of April. And you will, have a period of time to do that and then get that back to me. I still have only received about 7 or 8 people that have written to me telling me that they've seen the first 5 videos. But we're almost done with the videos. Then we've got a couple other things to do, and we're done with the course, right? But today, what I want to do is I want to look at a more complicated AC network theory that includes both series and parallel components, and then work through that and see how all of these things all work out. So this is going to take 2 lectures. The first one to really set the whole thing up, and then the second one to find the voltages and the currents throughout the entire circuit. So let's start at the beginning. Here is the circuit. I'm going to have a 100-volt peak circuit, and that's going to have a minus and a plus, obviously, and then that is going to go into what I'm going to say, at your level anyway, is a relatively complex looking circuit. And let me just roll all the things in here. This is going to be C1. This is going to be R1 and L1. I'll give you the values of those in just a minute. And then we've got R2. I hope you can see that. That's an R2. And then we're going to have another parallel branch, and that's going to include a resistor and a capacitor. So this is going to be R3, and this is going to be C2. And then we have one more branch of the system that's going to start off with an inductor, right? That'll be L2. And then that's going to go into a resistor in this branch, which is going to be R4. So this will be L2. Our frequency is going to be 10,000 hertz. That makes omega, which we know is 2 pi f, is going to be 62,830 radians per second, right? So we know that, and I chose that, and I want to give you the actual values of all of these various things. Both C1 and C2 are equal, and their values are 159.16 nanofarads. The reason that I chose that is because when you multiply 62,830 times 159.16 nanofarads, and then take the reciprocal of that, right, 1 over that, you get 100 ohms. We're going to see that in just a second, but let me just give you the values of the other things that we have in here. L1 is going to be 1.5 millihenries. And again, I chose that so that that would come out to be 100 ohms for L1. And then L2 is going to be 3.183 millihenries. And so that would be double that, and then that would come out there. So if we wanted to look at the, also let's get R1. R1 is going to be 100 ohms. R2 is going to be 200 ohms. R3 is going to be 200 ohms. And R4 is going to be 100 ohms. And let's just finish the rest of this. So if we wanted to see what the reactance of C1 and the reactance of C2 are going to be, that would just be -1 over omega C, right? -1 over omega C. So let's multiply that out. So we've got 62,830, that's omega, times C, which is 159.16, and that would be -9 for nano, right? Oh, I forgot to turn my calculator on. Well, that's fine, because I can still punch them all in. And I get, no, that's not right, is it? 159.16 nanofarads. Did I? Oh, I'm sorry, I forgot to take 1 over that, right? So that is 100. Yeah, so those would be 100 ohms. And what would be the angle? -90 degrees, right? Because it's going down on the complex plane. There's a minus there, so it's -J. Let's not forget what the impedance of a capacitor is. It's 0 plus J, and then -1 over omega C, right? Oh, that C, by the way, is not a subscript. That's actually C. So it's 100 ohms, and I'm just going to, that's why I chose these values. And let's do the same thing for the reactance of L1, right? That's just going to be omega times L1. And I think everybody can see that 62,830, I'll do it, 62,830 times 0.00159116 gives me 100. So there we go. So that's going to be 100 ohms, and then at positive 90 degrees, right? And if we were to look at the impedance of the second one, omega L2, and we can see that that's twice the value. So L2 is 3.1, so it's twice. So that's going to give me 200 ohms, and of course that's going to be at plus 90 degrees too, right? So we've really got our whole circuit laid out here for the frequency, and I think everybody can see how that's working out now. But let's just see how this is put together. So we come out of our source, our 100 volts peak source, and then we start going through that first capacitor. Now the first capacitor is in series with the rest of this, isn't it? So I really want to look at how I've got that laid out. So if I was looking at my total impedance for that whole circuit, I would look at the impedance of that first capacitor, C1, and then I would add that capacitor. And if you look here, I've got two different pathways, don't I? I've got this pathway here where I come to this junction. Let's call that A, and I'll call this B. Let's look at junction A now. Now, junction A is two parallel networks. It's got this network out here, and it's got this network here. So if we were going to say that those two are in parallel, then we really want to look at R1 plus L1. So if I have R1 plus L1, in fact, why don't I just write all of those out? So this is going to be the capacitance. I'm just going to put some parentheses and stuff in here. This is going to be the capacitance of Z of R1 plus Z of L1, right? In parallel. That's why I put these two lines there, because they mean in parallel. We're going to have to actually do all the math, but it's just telling us what we've got. Now, what do I have in parallel? Well, I've got R2 in series with these two things that are in parallel with one another. So this is going to be in parallel with, and actually, let me put some other brackets there. I probably could do without those brackets up front, and just a parentheses there. So that first branch that we have here is going to be in parallel with R2 in series, right? So we want a plus there, and I should have put Z of R2, but here I'll put that up there. Z of R2 is going to be in series with these other two parallels. So we have that in series with the parallel branches of Z of R3 plus Z of C2 in parallel with Z of L2 plus Z of R4, right? So that's what we've got. And I'll put a bracket around there so that we know all of the things that we've got here. So let's start looking and putting some of these things together. So Z of L2 plus Z of R4. Right, we've got that there, and we know that they're mutually exclusive as far as their resistance and the reactance. This is pure resistance, this is pure reactance. So, you know, we don't really have to worry about it. Now we know that L2 is going to be around 200 ohms, and R4 is 100 ohm. So what we really have is we have 100 plus J 200 ohms, right? Now, let's look at that and see what that really, if I've got 100 plus J 200, what is that really going to be? Well, in phasor format, I would square 100 and add it to the square of 200. Then I would take the square root of those two. The square root of 50,000 is what it actually come down to, right? Because 100 squared is 10,000 and 200 squared is 40,000. So it's a square root of 50,000. And the square root of 50,000 is 223.6 ohms. And then what is my angle? Well, the angle would be the 200 over the 100. Let's just draw the complex plane here for a second, right? So 200 and over 100. So I would have this angle right here, right? Here's the 200, and here's my 100, and that would be my angle right there. And how do I find that? Well, 200 is the opposite side, 100 is the adjacent side, and we take the inverse tangent of that. And so that gives me the inverse tangent of 200 divided by 100, which is really 2, right? The inverse tangent of 2 is 63.44 degrees. So there we go. We've got that one out of the way. Now, and both in its rectilinear complex number form and in its phasor form. So let's do the next one. Z of R3 plus Z of C2, right? Because that's this one right here. R3 and C2, and you can see that R3 is 200, right? R3 is 200, And then C2, which would be the same as C1, is just going to be 100. So if I wanted to write that, it would be 200 plus J, oops, excuse me, minus J 100 ohms. Can everybody see that? So instead, I've got them switched around, but of course, still square 200 and add it to the square of 100 and take the square root of that gives me the same number. That's going to be 223.6 ohms. But my angle is going to be different, isn't it? Because I've got a minus. Let me just change that. Make sure you know that's a minus J 100 ohms right there. And so this is going to be a minus angle, isn't it? And it's going to be minus 26.56 degrees. So we know what those two are, and hopefully that'll help us when we go about trying to put this all together. And let's not forget, if I have two branches in parallel, like I've got R3 and C2 in parallel with R4 and L2, how does that work? How do we find the equivalent impedance? So my equivalent impedance then is going to be the those two branches multiplied together divided by those two branches being added together. So let's just look at that. I'm going to do this one of two ways. So we can say with these two together that I've got 223.6 ohms at 63.44 degrees multiplied by 223.6 ohms at minus 26.56 degrees. Right, so I've got both of those divided by the two of those, so 200 minus J 100 plus, right, we're adding in the denominator, 100 plus J 200. I've used the phasor up top to do that, and I've used these on the bottom. I could have done it either way. I could have used phasors all the way across and them on the bottom. And in fact, I might even show you how to do that in the next step that we have, because if I just add these two up, right? That's what I wanted. That's what I want to look at. What am I actually going to get off the bottom? Now you can see 200 plus 100 is 300, and 200 minus 100 is 100. So that's 300. So this part right down here equals 300 plus J 100. And if I wanted to write that out, that would be 316.2 at an angle of 18.43 degrees. I'll let you verify that yourself, but we've got this up here, and really that's 223 times 223, and I think everybody knows what that is. 223.6 squared is 50,000, isn't it? So, and then I've got 63 minus that. So if we wanted to find out the equivalent for just these two, just those two in parallel at the end, we really have 50,000, right? And that would be ohms times ohms, so ohms squared. And then my angle off of that is going to be 36.88 degrees. And you're probably saying, well, that would be right. 63.44 plus a minus 26.56 gives me the 36.88, doesn't it, degrees? And then on bottom, well, we've already got that 316.2 and an angle of 18.43 degrees, right? So just for those two branches, if we wanted to find the equivalent of those two branches together, we end up getting 158.1 ohms at an angle of 18.43 degrees. Oh, actually, it's 18.45 degrees. It should actually, they both should have come out to like 18.44, but it doesn't matter. Now, we also know if we break that down, that gives us 150 plus J50 ohms. So just the equivalent between this series branch and this series branch, which are in parallel with one another, right, as far as the current goes, we get the equivalent of 150 plus J50 ohms. Now, how do I get back to, let's see if I can use some red pen. So we've basically got everything back to B. Now we want to go back to A. Well, how do I get back to A? Well, we've got a resistor here, R2, right? So if we were looking at the equivalent circuit up to that point, in other words, we've now done this section right here and gotten the equivalent for that. Well, don't we have to add it to R and then take that in as a parallel branch, two parallel branches? Yes. So let's add R to that. And we go to R2 and we see R2 is 200 ohms. Well, if I wanted to add 200 ohms to that, now I'm going to call this my equivalent at A. This would be my equivalent at B, right, at point B, and that would be everything that's downstream from B. My equivalent at A is just going to be to add that 200 ohm resistor to what I already have here. So that would give me 350, see, 150 plus 200 plus J50 ohms, right? That would be right there, right at that point, looking at everything that's going down here. So right at point A now, we have two different things. We've got to take that. So we know that we've got 350 plus J50 is going to be everything downstream from point A. And we know that this right here is just R1 plus L1. And we already know what R1 plus L1 is. R1 is 100. L1 is 100. So they're going to be 100 plus 100. So now we have this, right? We're going to have this in parallel with 100 plus J100. Now, we haven't gotten back to the beginning because we still haven't taken into account the impedance for C1, have we? No, we haven't. So if we put those two together, and really what we're doing is we're just multiplying the top, and then we're adding the bottom. So if I had 350 plus J50 and I multiplied that to 100 plus J100, and then I divided that by the addition of those two, which would be 450, right, plus J150. I think everybody can see, I don't have to go through that, everybody can see that that's those two added together. Now, when I add these two together, I can either work them all out, I could put it all out in phasor form now, and I would suggest that. I've done it one of two ways, and it's gone on for a long, but there are ways that you can now multiply this by the complex conjugate of the denominator. I'm going to hold back on that for a little while. You know, when we look at the 350 plus J150, now I'm just looking at my notes here to see if I did that all in my head. But I can tell you what that is going to come out to be. it's going to come out to be 120. So my equivalent thing at point A, just after the first, the impedance of the first capacitor, is going to be 120 plus J 26.667. Now, how did I get that? Boy, I wish I had enough room to put all of that on here, but I basically just took the 350 plus J150, turned it into, I multiplied these through, and then I multiplied by the ratio of the complex conjugate of this, which would be 450 minus J150 in the numerator and the denominator, and multiplied that through. That's how you get rid of a denominator in a fraction of complex numbers. But you can also do this, and the 120 plus J26, I'm sure is right. I could go back and do these. I don't actually have those in phasor form because I did it in the complex, the rectilinear form. Or wait a second, now what have I got here? I've got 200. Why do I have 200 plus J? Oh, is that 200? Wait a second. I should have gotten 250, shouldn't I? Where's that 3? Where? Just a second. I'm just looking at this. I think I took it off the wrong place. Oh no, that is right. That right before you get to it, it is going to be 120 plus J 26.66. And I did that one. Now that is 200. Wait a second. I've got that R. Oh yeah, I just want to make sure that I'm giving these. Okay, so after I added the R onto there, which was 100, that gave me 250 plus 150. I'm just looking at my notes here. That's the 150 plus J50 is fine. And then that should be 250 plus 150, shouldn't it? Because I'm only adding 100. That R2 I've just I'm just looking at my notes that I've got here. We did that one with no problem. Then we added on R2. Oh, wait a second. I did not add R2. In the right spot. Oh well, that's fine. We can still we're still doing it this way. But let's go back and look at this now. Now we know that we've got the 150 plus J50 there. And then what we have to do is we have to add on R2. So R2 being 200, that gave me the, well, this didn't come out right then. That would not be right. So I've got the 200 on there. So that gives me 350 plus J 50, right? I just want to make sure that I've got those are in parallel plus the R2. So that gives me 350 plus J50. And that is going to be in parallel with the 100 plus 100 that I've got right here. And we're multiplying it through, and that's going to give us our impedance. Now this, I'm just going to wipe that out for a second. I would say stay ahead of me, but I'm not even sure where I'm going. All right, I'm kidding. But let's just work a couple of these out, and then we'll have that at A, and then all we have to do is add the impedance at C. And that's where I want to get us before I do the second lecture where we actually find out. So we're trying to find the total impedance of that circuit going back to the source. So let's just do a couple of these so that we can work them out. If I have 350 plus J, oops, turn the calculator on. So 350 squared plus 50 squared taken to the square root gives me 353.6 at an angle of just a second. I know, I'm even worse than you guys are. At 8.1 degrees. And then 100 at 100 is going to give me 141 at an angle of 45 degrees, right? And then 450 on the bottom plus 150, let's do that. 450 plus 150. And that gives me 474. So let's just write these out. So 353.6, that's a 3, at 8.1 degrees times 141 ohms at 45 degrees divided by 474.3 ohms at 18.44 degrees. All right. So we have all of those. Let's figure out what our impedance is going to be right at this point. Now, we still haven't added the impedance for that first capacitor. We haven't done that, but we're going to find out what it is right at that point because we're now putting those two in parallel with each other, just like we've got there. So 353 times 141 divided by 474.3 equals 105 approximately. So I'm going to say 105.0 with a line over the top of the 0, right? And then an angle of 8.1 plus 45, 8.1 plus 45, right, equals minus 18.44. And I think everybody sees why I've done the minus. So that's 34.66 degrees. And of course, those are ohms. Now, we're not done yet because we've got 105 ohms at 34.66, right? 8 plus that minus that gives me that. And we still have to take into account the impedance of the capacitor. So to find out my total impedance now, I'm going to have the impedance of that first capacitor, and we know that's 100 ohms, so it's going to be 0 minus J 100 ohms, right? And we want to add that to this one that we've got right here, the 105 at 34.66. So let's do that. 105 times the cosine of 34.66 gives us 86.36. And then if I take 105 and I multiply that by the sine of 34.66, I end up getting 59.71. So plus J 59.71. And of course, those are ohms too. So let's add these up. Well, 0 plus 86.36 gives us 86.36 ohms. And minus 100 plus 59.71 gives us minus J 40.3 ohms. And now let's just change that into what it is. So 40.3 squared plus 86.36 squared equals, taken to the square root, 95.3. 95.3 ohms at an angle of, well, let's do it's minus 40. Don't forget that. You know, your calculator won't know where that minus is. But I've got 40.3 divided by 86.36. And then if I take the inverse function, that's going to tell me it's at minus 25 degrees. And in fact, it's minus 24 or 25.0, so it's very, very close. So in the end, we get 95.3 ohms at minus 25 degrees. Now that's my total impedance as I go through that. Let's go back again and just sort of look at this and see what we've done before I end the lecture and go on and start finding out all the voltages at A, the voltages at B. So what I want to do is I want to find out the current, right, that's going through there, because I know that I've got 100 volts peak at 0 degrees divided by 95.3 ohms at minus 25 degrees, right? So the current that's going to be going through that circuit is going to be 1.05 amps peak, and the angle is 0 minus a minus 25, so that's going to give me a positive 25, isn't it? Because minus a minus is you know, cancels it out. I just want to check some things here with you to make sure that we've done everything right. We came down here first and we found the equivalency between these two circuits, and we multiplied them on top just like we did in DC, and then we added them on bottom so that we could take those two different branches and we could find out the equivalent impedance. And we got that equivalent impedance was 150 plus J50, right? That's the two of those. What we had to do after that is we had to add R2 onto that. And so when we add R2 onto that, which is 200 ohms, that gives us 350 plus J50. And then that brings us back to point A. Now at point A, we now have this one that is in parallel with this one, right? So this whole branch over here is now in parallel with that branch there. And so we put the two of them, the 350 plus J50, in parallel with the 100 plus J100, and that's what we've got here. And we figured out what their phasors were, so we could multiply those together. And then we also figure out what the phasor of this one on bottom is, the addition of those two, 350 plus 100 and 100 plus 50, and that gave us this. Now, when we figured out those, because multiplying those together and dividing them by the addition of those, or the sum of those two, that gave us the 105 at 34.66. And then we had to add on the impedance of the capacitor in the beginning to that, and that gave us this. And that's what it is in phasor form. And to find the current at that frequency, we just divided the voltage divided by that. And of course, let's never forget Ohm's law, V equals IZ, right? And now you're saying, well, now we got the current. We know what the thing is. So we should be able to use that current information and Ohm's law, right, to find out what the voltage drops are, the voltage drop across that first capacitor. If we can find the voltage drop across that capacitor, and what is the voltage drop across that capacitor? That voltage drop across that first capacitor is just going to be the current times the impedance of the first capacitor, isn't it? And we're going to work on that in the next lecture and find out what the voltages and their phase shifts, right? Because these voltages are not just a number anymore. They're a number at the phase shifts. They're a complex number. Let's remember that. And so we're going to find it out at A, and we're going to find out the voltage at B. And I think we also want to find out the voltage at C, which actually is going to be easier than finding it out at A or B. But that's what we want to find out. Now, what else do we want to find out? We want to find out all of the currents that are flowing. The current that's flowing out of there is the same current that's flowing in there. I'll call that I1. And in fact, we found I1. We could call this I1 right here, couldn't we? So we know what I1 is, but I also want to find out what the current through that branch of the circuit is. What's the current through R2? What's the current through R3 and C2? And then what is the current through that last branch of the circuit? And once we know that current through the last branch and we know the voltage at B, right? We know the voltage at B, we know the current through this last one. Then we can find the voltage drop across that first inductor. You know, I probably shouldn't call that C, should I? Why don't I call it D? Because C might get you confused with the capacitors in the circuit. So I'll call that point D. And D, of course, is going to be. So that's what our next and last lecture is going to be. So I'm going to stop this here, and then I'm going to do the other lecture in a little while, because I'm going to have that cup of coffee, because I've been talking for like 40 minutes nonstop now. Now, where is the end of this? There it is.